In example 5.2, we have a bottle submerged in water with some sand at the bottom of the water. Now, we know that different forces act on this bottle. So the first force will be the weight force, which is equals to m times g. The second force will be equals to the buoyancy force. The buoyancy force is equals to the amount of water that has been moved times. Actually, let me write it. Let me write it better first of all. We have the amount of water moved that I'm going to use this sign for, times the uh, area times the depth at which is moved, so the volume, times the acceleration, because we know it's a force. So this one is pretty much equals to m of water that has been moved, because this one is equals to volume. So now we know that at d naught we have equilibrium. So it means that these two forces that we have, so weight and buoyancy force, are equal to each other. Therefore, we have mg that is equals to the uh, density of water times the area times the depth times the acceleration. So starting from this, then we can say that there is a displacement that we can call x that is up and down. Let me draw on our thing. So here's d0. So this is, sorry, let me write it there. So this one will be d0. And then we have displacement. So we can, for example, call this one x on either side. And x is going to be the amplitude. Let me color code everything. So x is going to be equal to the amplitude. So what we know is that in this case the amplitude is also dependent on the O. So our buoyancy force will depend on the amplitude. So first of all, the density of water times the area times the depth. Actually, the depth changes. So we're saying so the acceleration times the depth, and the depth will be d naught plus or minus, in our case, x. In this case, we say minus because x will be a absolute value, whether it goes up or down. So we're talking about amplitude. And the weight doesn't change, but we can put it equals to the weight because we said they have to be the same. So now let's look. We have the density of water times the area times the acceleration times the first d naught, so when it's at perfect equilibrium, minus the density of water times the area times the acceleration times the displacement from the equilibrium position. So the amplitude equals to always mg. Now we said from before that mg is the same as this. So we can say that these two are the same thing, so they can actually cancel out. So the only force remaining is this part over here. So the density of water times the area times the acceleration times the displacement is equals to the force left. And that is all we have left from all this. So what does this mean? Well, it means that our force, which is also mx double dot, is going to be equals to, so we have the x double dot is equals to negative density of the water times the area times the acceleration times the amplitude over the mass. But now let's go back and let's look at the very first formula, one of the first formula we wrote. So this one right here. So from this, we know that we know. I'm sorry, 1 second. We know that G. In this case, we have to call it E naught because that's the initial one. So we have G over D naught equals to the density of the water times the area times the acceleration over the mass. Now this one looks a little weird, but if you go back and look what we have right here, you can see why I'm writing like that. So here we can rewrite it as the only thing that is not actually part of it is the x. So the x is the only thing that's going to be saved. So here we're going to have negative g over d naught, and then the x. Now we know that usually the formula is going to be equals to negative the angular velocity squared times the amplitude, which will be a. But we said that x is equals to a, and so the angular velocity squared is equals to g over d naught. So the angular velocity is actually going to be equal to square root of g over d naught. And that is how our formula is actually proving right. So we have an acceleration over a distance, and that is our angular velocity. And of course, the amplitude is a, because we said that's from the beginning, that's the amplitude x. So now we can find the period very easily. By saying the period t is always going to be equal to 2 pi over the angular velocity, which we said is 2 pi divided by this value over here. So I will probably paste it over here. So it's equals to 2 pi times square root of d naught over g, because it's with the bottom and the top. So now in our case, we're given that E naught is equals to 20 centimeters. D naught, sorry, is equals to 20 centimeters. So we're going to have 0.2 meters divided by 9.81, which then equals to 0.9 seconds. And that is our period.